And then all those questions that say, here is a solution, I'm doing something to that solution, find an answer, okay? On Tuesday, I'm going to tell you that you cannot trust concentration in the presence of a contaminant. So after today, we're cutting this off, and we're going to use concentration two ways. One is just straight up, I trust you. And then after today, it's, well, I might not trust you. So the titration that we did today, you added sodium hydroxide to acetic acid.
Yes.
And everything's fine, because those are the only two things in solution. Then you added an indicator. Now, does your indicator, because it's a contaminant, influence the end point of the reaction? We don't know. Maybe it does, maybe it doesn't. That's what next week's about. Okay? So let's go look at, oh, it just started recording again. I'm going to leave it recording, because I probably said something useful.
No.
No. Well, we're going
I
to...
said, I don't know.
We'll cover it all.
No,
We'll
yeah.
cover it all again later. Okay. So, what we did with the precipitation titration, where we looked at the concentrations in solution before the event of equivalence, at the event of equivalence, and then after equivalence, is applicable to any reaction in which you mix two things together, not all together in the same quantities, but you add one progressively. Okay, so if you can do it for what we've done it with, you can do it for acids and bases, and in many cases acids and bases are easier. Okay. Let's go talk about two more things. One's still in the world of precipitations, and one is acids and bases, but is one of the dibasic ones, diprotic ones. We'll see. Okay. Come on, baby. I know what we're going to do in lab next week. What we're going to do in lab next week is the next, after this topic, it's the next thing that I'm going to talk about. One of these has got to be in your future. I've got a lab somewhere where we're going to put a couple of things in solution, and you will slowly add a chemical, and it will cause one of them to precipitate and not the other. So we will do a fractional precipitation in lab. All right, things we know. If I've got two salts in solution, the salt with the lowest KSP precipitates first. I'm not sure if I said it on camera on Tuesday. I think I did. Part of when we do this in lab, this will be stirred. This will be agitated, because you need the diffusion effect of, say this is like what we did on the board the other day, silver and iodide versus silver and chloride. The silver iodide is what is it, 10 million times more insoluble than silver chloride. So we would spin that, let the iodide interact with the silvers, 10 million times more insoluble. It will precipitate and leave the chloride still floating around. Okay? okay? And when all the iodide is gone, then the chloride will precipitate out. If we did it rapidly by adding a lot of silver to the mixture of chloride and iodide, then as the iodide just grabs hold of everything and falls to the bottom of the flask, it will drag chloride with it. So we need that to be agitated. Sometimes people might also want to warm that, because cooling things down makes everything, all solids, be less soluble. So who are you helping and who are you hurting if you just make everything cold? If you made everything cold, then everything is less soluble than it would be at room temperature. So if we can warm it up a bit, you can make the really insoluble thing precipitate and leave the other stuff behind. We'll look at those tricks in lab when we get there next week. All right, here's a question. Can a solution of 0.010 molar lead iodide be separated from mercury iodide? Mercury is one of those complicated ions. It makes a couple of things. This is the iodide. If you make this be a chloride, it's called calomel, and it's this thick white solid precipitate. But that's clearly mercury in the +1, which is not a common oxidation state for anything outside of group 1. That's going to need concentration as well. Can I separate a 0.01 molar solution of lead iodide from a 0.01 molar solution of mercury iodide at an efficiency of 99.99%? I would probably want to call that a selectivity. A selective precipitation. Okay, we need a couple of pieces of information. KSP for lead iodide is 7.9 times 10 to the -9. Comment on the magnitude of KSP?
It's small.
It's small. That is 10 to the -9 is 1 billionth. KSP for mercury iodide is 4.6 times 10 to the -29. Yes. Probably a good thing. It's probably a good thing that the mercuries and the cadmiums and the leads of this world are insoluble, because we do not want them in our water supply. We absolutely don't. Okay. Comment on the magnitude of that.
Extremely small.
Yeah, that is really, 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 really small. That is a 0, a decimal point, and then 28 additional zeros before you hit the 4. Okay. At 99.99%, here's what that means. 99.99% selective precipitation It only says separated. Which one precipitates first? The one with the lowest KSP precipitates first. So we will, at this percentage, we will leave behind 0.01% of what you've got. And what have I got? I've got that. What is 0.00? What is 0.01% of 0.01? Roll,
Oh,
please.
like 0.0001.
One divided by 2.
Wait. What is it? What does percent mean? No, percent. Not times by 100.
So when you
Divide by 100.
if you plant some.
If I give 5% of my yearly salary to Wiener Dog Rescue, which no, but it's, but you know, we do. We support Wiener Dog Rescue. I don't know. My wife has a direct debit out of her salary that goes to saving taxes. Yeah, if I gave away 5% of my salary, it would be $5 out of every $100 that I make. So percent literally means divide by 100. How much are we talking about here? 0.01% of 0.01. What is that?
That's the -4 or 0.0001.
Okay,
If you subtract it from.
that's just this part of the number.
Ah.
And I'm doing it to this number.
Mhm. 0.099, right?
0.009.
Yeah, like that. Huh?
No,
You don't subtract it from it?
no.
What?
If that's the percentage, you don't subtract it from.
Not subtract from. No. No. Okay.
I'm confused now.
All right.
Okay, go back.
You have $1,000.
Yes, yes.
You won $1,000 in the lottery.
Nice.
You have to give 35% of it to the government.
Yes. You have to give away $350, right?
How'd you figure that?
Because I just imagined it as 100, took 35 and multiplied it back by 10. I was being lazy.
35% means 35 divided by 100, and then multiply by that number.
Okay. Ah, so it's even smaller. It's 1 to the -6, right? 0.000001.
We got there.
Oh my god.
To selectively remove 99.99% of this one. No. Did I say chloride? It's iodide. Why did I write chloride? I think I was talking about calomel. I was, wasn't I?
Yeah.
And then I just subliminally wrote the wrong thing down. They have to both be iodides because we're going to add iodide to a solution of lead ions and mercury ions. Okay. To remove 99.99% means to leave behind 0.01%. Take the number, divide it by 100, multiply it into the other number. And that means I'm going to leave behind a solution that is 1 micromolar. Okay. Now, the thing that is the least soluble is what we need to be thinking about right now. Not the one that is most soluble, but thinking about this one. And this is in solution with its ions.
Wouldn't there be 2 Ag?
Oh, do you know what?
Or did you just ions different?
Let me check whether they've given you Mercury 1 or Mercury 2. Because I want to write Mercury 2. I want, yeah. I've written Mercury 1 in my notes. Let's get this right, because right now there is a disagreement on the board. And that won't do. It is Mercury 1. Oh, you know what they've done? There you go. That's clever. That's clever. This is awkward. You need inorganic chemistry 2 to actually get here. This is not 2 mercury pluses.
Okay.
It's a dimer. It's a mercury and a mercury stuck together with an overall 2+ charge.
Oh.
Complicated. We would really have to explain that to you. Okay.
That's called a dimer?
Mm-hmm. 2 things stuck together is a dimer. And it happens a lot here on the periodic table. And it happens so much here on the periodic table that we don't bother changing the labels on the bottle. So you can buy BH3, it's called borane. It says borane on the bottle, BH3. It does not exist. It is B2H6. It's 2 of them stuck together. You can buy AlCl3. Doesn't exist. It's Al2Cl6. It's not going to stop you from buying it. There's a whole bunch of stuff. It's here in the periodic table, not too far from there. And we just kind of go with it. Okay. So this is a lump, and that is 2 lumps. Okay. That is going to make our math different than if it were 2 individual mercury 1s.
Okay.
Okay. All right. I didn't notice that when I first picked this out. I'm sure there's another simpler version somewhere else. Okay, so that gets to be one thing. And the iodide gets to be raised to the power of 2 because it was 2 things. We always raise the concentrations to the power of the coefficients in the balanced equation. All right. That's what we know. And again, if we were ever going to give you this, this would come with a note that says calomel, or whatever the iodide of calomel is, breaks apart this way. All right, go ahead and find the concentration of iodide you need to make this happen. So the value that you're finding is the value that precipitates everything except that final 0.01%. The numbers are there. It's not obvious, but if you think hard enough, the numbers are there. So have a go at it. And when you are close to an answer, let's share our answers amongst each other and figure out how we get there. Just added a clue to the board. Okay. I have 2 salts. I have a lead salt. I have lead and mercury in solution, both at the same time. If I add iodide, they will both precipitate eventually. But the KSP for the mercury iodide is so much lower than that for lead that it should precipitate first as long as I use my correct method. The question says, can you get 99.99% of the what? Mercury out, which means you are leaving 0.01% behind. 0.01% of what? The mercury. So, this, we know this. We know that. Do I know the value of KSP? Yes. Do I know the value of this?
Yes, no, maybe, yes. Okay.
That's how much is left behind. Do I know this?
Not yet.
No, that's what the question is asking. Go find it. Run up chemistry. Yeah. So much of what we're about to enter into is there are two things occupying the same space. If I know the value of one of them, don't I sort of automatically know the value of the other one? Like, if I've got 10 coins in my hand, and I tell you that they are either nickels or dimes, 4 of them are nickels. How much money have I got in my hand? So let's actually rewind. 10 coins in my hand.
Yes.
4 of them, they're either nickels or dimes.
So they're all either nickels or
They're all either nickels or dimes. There's no quarters, no half dollars, no dollars, no pennies. I've got this great lab for you to do, where you can count pennies. 10 coins. They're either nickels or dimes. Nickels are worth how much?
5 cents.
Are they?
Yes.
Okay. And dimes are worth how much?
10 cents.
Okay. 4 of them are, what did I say?
Nickels.
4 of them are nickels.
What do you say?
So 4 times 5 cents is 20 cents.
Yes.
Which means the remaining coins are all nickels. Yeah, no, dimes. And
six
there's
left.
6 of them.
Whatever 10 is 60 cents. So you have
Mhm.
80 cents in here.
80 cents. Okay. I did that with incomplete information.
Okay. Yeah.
Okay, I see.
So, why are we multiplying, why are we having the mercury be the 1 to the negative 6? Not like, for example, okay. But if we want to leave behind, yeah,
This one precipitates first.
yes, I understand.
That one precipitates first.
Mm-hmm.
I would be very famous and very rich if I could find a way to make that one precipitate before this one.
No, I get that. I think it's just the number.
Is it cause we know the
'Cause-
metal's gonna be the one that's gonna precipitate?
No, it's just the percentage of that, so why don't we do, for example, like, the big, so for example, I were to subtract 0.01 minus the 1 to the negative 6, why don't we do that number instead of
See,
that
I was
number?
trying to do the same.
Cause I did that
I was
first.
trying to do the same thing.
Like, so, cause if we wanna get rid of, okay. If we wanna get
It
rid of.
makes sense, but it's still trying to click on my.
Okay. Couple of little things that might help. State symbols. This side of the equilibrium, you're in solution.
Mm-hmm.
That side of the equilibrium, you are not.
Mm-hmm.
To be a concentration means you're in solution. Okay, so this is this mercury iodide.
No.
No, because it's ionic, so it splits apart.
Okay. Okay.
That's the concentration of the mercury that's in solution. It's also the concentration of the lead, but that's going to come out later.
Okay, I get it now. Mm-hmm.
If I take 99.99% of it away,
And put it into the solid.
I get that much that is left behind.
And we're looking.
Everything else has gone into the solid.
And we're looking for the point at which that equilibrium, like that KSP, and is at that point, and so we
Yes.
have to. Okay, I get it.
Yes. Okay, so we know this number. This number, I'll just do the algebra first. I squared is KSP over HG2 2+, right? Done that right? Move this across, or what you young Americans say, divide both sides by the same value. So that means that the iodide concentration is the root of KSP, and KSP is in the question. 4.6 times 10 to the negative 29, divided by the concentration that is still in solution
That way one.
at this particular part of the question.
Yes.
Okay. You have a number?
I do.
You all have a number?
Yeah.
Okay, wait, share your number. Make sure it's the same number. Does it have an 8 in it?
Yes,
In there.
yeah.
Does it have a 10 in it?
10 to the.
So it's like. Dr. McGuire, I'm about to ask a really dumb question.
I
So-
love dumb questions.
My brain is not working.
Yeah.
Okay, so I understand the part that if 99.99% of the mercury iodide
Mm-hmm.
comes out.
Yeah.
And I recognize that mercury and iodine are both in solution, but how do you know specifically that the 1 times 10 to the negative 6 is mercury and not mercury and iodine? That's what's confusing me. Like my brain is shut off today.
Okay. And your number is? 6.8. Okay, so we have a concentration of iodide that is 6.8 times 10 to the negative 12. And that's a concentration, so it needs a unit. Okay. As an aside, how do we know what the label is telling us? If I have a bottle, and you'll have seen me do this before, and it says 1 molar HCl, and it is full up to the 1 liter mark. How many moles of HCl are in the bottle?
There's 1 liter somewhere.
No.
Oh, because it's.
There is no HCl in that bottle. None. No HCl in that bottle. It's ionic, and when it dissolves, it makes H plus and Cl minus. It's a strong acid. And the H plus has no interest in ever getting back together with the chloride. Never, ever, ever getting back together. There's no HCl in that solution,
Okay.
because it's ionic.
Yes.
Okay. What if it says 1 molar calcium nitrate? How many moles of calcium nitrate are in this 1 liter bottle of
None.
calcium
None.
nitrate?
None.
None.
There's none.
But how much calcium is in there?
Well, calcium. 2 plus.
2 plus.
Yes. Has 1 more.
It's 1 mole of calcium, 2 plus ions. How much nitrate is in there?
3.
2. No, it's 1/2. Wait.
No, 2 because of the.
Okay.
Nitrates are NO3 minus, calcium's a Ca2 plus. So in this solution, there is 1 mole of that, but 2 moles of this.
Yes.
When we're thinking about things in solution, we should be thinking about the ions, not the collective
Okay.
quantity. When you put this into solution, knowing what we know about the way that it acts as a blob and not 2 individual mercury 1 pluses, then that's how much there is while it's in solution. Okay, and twice as much for the iodides when they are in solution. Okay. Okay. Have we answered the question?
We
that right there.
have found I minus. We found that part of the
Okay,
question.
why would I want to find I minus?
To see if we can even precipitate or separate that at all, because is it too small? I don't know.
So, will an iodide concentration equal to 6.8 times 10 to the negative 12 moles per liter cause lead 2 plus to precipitate? K is the concentration of products divided by reactants. Yes? In all circumstances? Under all concentrations?
Well, there's no solids or.
Okay.
And in the KSP equation, there is typically no reactants.
Mm-hmm. But K, just in general, is, and if you made a KC, then you could say, oh yeah, it's just concentrations. Is products divided by reactants. But the question is, at every concentration of every reactant and every product, is that true? No. This is only true at the equilibrium concentrations. Values of concentrations of products divided by reactants that are not at equilibrium are not given the value K, they are given the value Q. So, that is only true at equilibrium. At non-equilibrium concentrations, Q is products divided by reactants. Now, we're doing KSP today. We could be doing KA tomorrow.
Are we ever doing KB in this course?
We should probably do one because we kind of skipped it in chemistry too. KB is
It's basically just inverse of acid.
yes, it is valid. It is a number. You can look it up. But
It's like it's like
I know
basic.
what the purpose is.
using KB means you now need a table for the values of KB.
Yeah.
Why don't you just have a big table that only has KAs?
Cause then you know which ones are really basic.
Because then you don't know which one, whether it's an acid or a base. So there's two schools of thought, one of which is horribly, horribly wrong. Yeah.
That's unfortunate.
So when it's a KB, it actually tells you how to use it. Because it's KB, when it's KA, it tells you how to use it. But it could all go in one table. They could all be KAs. All right. We have three possibilities. Q is bigger than K. Q is K. Q is less than K.
Is this where the saturation comes in?
Yes. Q is K, we're in equilibrium. Which one of these causes precipitation? That one. This one means no precipitation. All right, let's go find Q. And then compare it to its value of K. So the deal with Q is it is in exactly the same form as however you had expressed K, but the numbers that you put in are numbers that are experimental. They come from bound data collection, and they might not necessarily be at equilibrium. So our Q ends up being, because now we're asking the question about, our question has shifted, and it's asking now about lead. Q gets to be whatever the KSP for lead would be. KSP for lead would be PP 2 plus I minus squared, right? Because PBI2 is in equilibrium with PP2, that's a solid. This is the aqueous solution, and that is 2 iodides. Okay? So Q follows the same language that K does. Let's see. Do we know that value?
But we just found an I minus.
But we do know then, but we do know from the beginning of the class,
That is the concentration of lead ions in solution. That one, right there. So that goes here. And for iodide, didn't we just find that?
Yes, we did.
Is it still on the board?
No.
There it is. It's hiding. In our special case, this is 6.8 times 10 to the negative 12 moles per liter. And I'm going to square that. Okay? So, find out what the value of Q is. I can guarantee it's got a 6. Oh no, maybe no. No. I saw the 0.1 and thought, oh, it's going to have a 6 in it. But then we're squaring it. KSP is in the question for lead.
7.9 times 10 to the
So I'm going to specifically say for the lead. And it is 7.9 times 10 to the 9. Negative 9. All right, do we get the value of Q?
We got 4.6 times 10 to the negative 25th.
Are you That's not the number I've got in my notes. You didn't square it.
4.6 times 10 to the negative 26. Yeah, that's fine.
Okay, let me take a look. Oh yeah, you know what? Give me a pen, pencil. I gotta make a note to myself. Oh, I pressed the button once and all of that came out.
Yeah, it's okay. I'm not worried about it.
Right. 4.6 times 10 to the negative 25.
Yes.
Okay. No.
Because it's a cube.
Yeah, K's. Values of equilibrium constants do have units, but they are so messy, and they are for each individual case. Every time you do a K calculation, you would have a completely new set of units. So we've just given up and just said the number. The number explains, are you to the right or to the left? This number is to the left. This number is further to the left. Okay. Is Q larger or smaller than K?
Smaller, like a lot.
Q is a lot smaller than K. So the outcome to the question of does the lead precipitate? Okay, so there is no precipitation of lead. To the original question, can the mercury be separated from the lead
Yes.
at that level of certainty?
Yes.
Yes, it can.
Mm.
Okay.
Are they compounds? Like the lead iodide and the mercury iodide? Are they compounds?
Yeah, because they're ionic.
Okay.
We call
Yeah.
combinations that have combined because of ionic bonding, those are compounds.
Those are compounds.
And if you are a collection of covalent bonds,
Yeah.
then you're a molecule.
Molecules, yes.
And molecules are made of non-metals.
Yes.
Hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur. Once you start throwing metals in, then I've got left-hand side of the periodic table, right-hand side of the periodic table. I've got ionic
Which are
going on.
What about with how we did like the coordination chemistry? Was that still?
Those are complex ions, so it's still ionic, but complicated. Okay. All right, I'm going to show you what we're headed to. We didn't get both of these in today. I thought we would.
We asked
Yeah, no, no, we did it slowly. It's fine. I'm not worried. We've got a number of topics to hit, and they all require explanation. Okay? So I'm not worried about galloping through the textbook. We're going to pick a couple of topics and describe them. Let's set this one up. And you will do this or something very like it in lab next week. I have a mixture. It's a solid mixture. It contains this, called,
Sodium carbonate.
and this. It used to be called bicarbonate. We don't call it that anymore. You can still buy it called bicarbonate. That's sodium hydrogen carbonate.
Okay.
Okay?
I was like, there ain't no ways of sodium hydrogen.
It requires 29.11 milliliters of 0.734 moles per liter hydrochloric acid for a complete titration of everything in solution. Let's write both of the titration reactions down side by side. HCl plus Na2CO3 double displacement. Group 1, Group 1. Both ionic. Group 1, Group 7, Group 1, so 2 plus 1 cations and a 2 minus anion. Good, so I need 2 of those. Makes 2, no, H2CO3 and 2 NaCls. Okay. What happens when you add acid to carbonate? So I should have written them in the other order. The H2CO3 that you generate turns into a carbon dioxide and a water. Because nature would just rather have it that way. And that's an AQ, and that's a gas, and that's a liquid. And when we do the hydrogen carbonate, now I've only got one ion to do the double displacement with. So I make 1 sodium chloride, and then I make the H2CO3, which decomposes to carbon dioxide gas and water. Okay? All right. I have 2 equations. And the mass, right here, can only belong to either of those. If I had 10 coins and they were either dimes or nickels,
Yes.
and 4 of them gonna do. I'm going to make the mass of, pick one,
NaHCO3.
2A. The mass of that be equal to X grams. Three dots in a triangle means therefore. The mass of NaHCO3 is equal to what if the mass can come only from one of these two? What if it was all hydrogen carbonate? How much would I have?
1.372.
Okay, minus 0 when X is 0, because I've got none of this. What if I had a gram of that? If X is 1 gram, then I would have 1.372 minus the 1 gram.
Okay.
Oh, so 1.372 grams minus the other number. The moles of Na2CO3 is the mass of Na2CO3 divided by its formula mass, which is X grams divided by sodium's 23 point what?
0102. I know that.
22.99.
Oh yeah. Hydrogens are 1.00.
Hydrogen is 1.008.
Carbons are 12.0.
Carbon is 12.01. Oxygen is 15.999.
84. Wait. Oh, we're making Na2 here. Oh yeah, I got 105 on there.
Take away sodium, add a hydrogen. Taking away 23 and adding 1. I'll get you as far as the logic goes and then leave you to do the rearranging. All right, moles. As we know that molarity is moles per liter, right? So moles is molarity times liters. and we have a molarity and a volume in the question. That volume cannot continue forward as milliliters, it must be converted into liters. And it's odd number, 0.734 moles per liter. And the per liter and the liter cancel, and the milliliter per milliliter and the milliliter cancel, and that gives me a number that's in moles. I think I've got a fourth. I'm keeping lots of digits in. Okay. So we know a couple of things. We've got this set up. If I find one of the numbers, I'll find the other number, because there's only two things. And it's either or. And they both react with HCl, but they don't react with HCl evenly. One of them reacts with HCl twice as much as the other one does. Okay, but the total number of moles consumed is the total number of moles consumed. And the moles of HCl consumed has to be equal to the moles of sodium carbonate and the moles of sodium hydrogen carbonate that are also consumed. Okay? The HCl that you consume has to be equal to the moles of carbonate and hydrogen carbonate that are also consumed, and they are not consumed in equal amounts. We don't know what particular, we know what the mole ratios are going to be, but we don't know what those necessary numbers are. Okay. So 2 times x over 105.99, because that's the number of moles of this, plus 1 times 1.372 minus x over 84.01 is equal to 0.02138. Go find the value of x. Can you do it now? No, this is a take-home question. I did it. Now, when I do a calculation, I like to break it down step by step. If you zoom in on the video, you'll be able to see it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 steps. 14 steps of algebra. It's just shuffle this over here, shuffle this back, shuffle this over here, shuffle it back. Divide by the log of the first number that you thought of. Can be done. have a stab at it, and we'll finish this up on the board on Tuesday. And then you're in for a disappointment. Concentration is real.
Oh, yeah, you've already told us that, I don't like that.
It's, concentration is real as long as there's nothing else in solution with you. This is a question that might require further scrutiny, because this is in solution with that. And does something being in solution with something else affect its ability to stay in solution? Maybe yes, maybe no. Okay, I'll post this in the next day.